In Chemistry 1, we're going to discuss three broad categories of bonding. Two of these we'll talk about in great detail throughout the semester. One of them we'll bring up frequently, but we're not going to go into the great detail on because it's either really obvious and easy, or talking about it is really complicated and nasty, and we leave it for upper level or graduate level classes. Now, let's take a look at these three categories. The first one is going to be ionic bonding. That's going to be the case where one atom is going to completely transfer an electron to another atom. They're going to stop having that electron be shared at all. It's just a straight transfer. So this atom that lost an electron becomes a cation, a positive charge. The one that gained a new electron is going to be an anion with a negative charge. And notice what happened to their sizes. Our cation got smaller, as we expect, and the one that became an anion got slightly larger, but only a little bit, which is also something we anticipate. Now, when you have a full-size positive and a full-size negative charge, they're going to attract each other and they're going to stick very tightly. Now, most of the time, that means they're going to end up being a solid. The reason is they're sticking together so well, they don't pop loose and they don't wiggle much. Now, that said, one of the more recent topics in chemistry, probably the last 20 years or so, when we're doing our research, is a category of substances called ionic liquids. You can have liquids that are ionic. They're less common, dramatically less common. We have a decent set of them now, so it's not like there's only 2 or 3 of these things, but compared in ratio to the rest of the chemicals we know about, it's a small subset. So I'll mention that they do exist, but we're not going to talk about them in our course. For our purposes, it's enough to think of ionic bonding as typically leading to a solid. Now, this is going to be, in terms of the electron and the energies involved, this kind of a scenario. One where one atom has completely stolen the electron from some other atom. There will be no sharing. One has completely lost it, the other one has completely gained it, and they're both going to end up being stable in that result. There's not going to be a change. Sharing, not so much. It's more theft or donation. Now, in our second example, we're going to have covalent bonding. And this is going to be a case where they're going to be sharing, their valence, valent, electrons. Now, it may not be all of their valence electrons, but they're going to at least come together to share some of them. And we see that here in chlorine and bromine when they come together. Both of them are in group 7, the halogens. That means they both have 7 valence electrons. That's not an octet. We know you get a special moment of stability if you have an octet of electrons. Well, chlorine says to bromine, "Hello there. Can I share one of those electrons with you? It'd make me thrilled." Bromine says, "Not a bad plan if you share one back with me." They get together, they have a couple of drinks, and a few years down the line, they both end up being well married. That's my analogy for it, at least. You got your two atoms, they're coming together, they're depositing their electrons at the electron bank, FDAC. And now they have something that they're sharing, and it's hard to pull them apart because it's really hard to divide up those assets. Hopefully, there's more reasons than that for them, but they're atoms, so probably not. That's going to be an example of covalent bonding, and an analogy to think through it with. Now, our third case is going to be metallic bonding. This is the one that's either really straightforward or really complicated. Now, what's going on here is that all of your atoms end up sharing some of their electrons. Every one of them is sharing some of their electrons. And so they end up having this sea of electrons that gets exchanged between all of the atoms. That makes them all really, really stable. My analogy for that is kind of like, it's the communist view of the electron. They've all put together their electrons, they're all sharing the electrons. Well, great, we've got 3 analogies, but how does that tie back to properties that we already know about? Let's connect this all back to ionization energy and electron affinity. So for ionic bonding, we're going to have a metal with low ionization energy. It means that it's very easy for this one to give up an electron. Then we're going to have a nonmetal that has high electron affinity. It's going to be very good at taking the electron. And as a result, they both become more stable by sharing their electrons. Now for covalent bonding, what we're trying to do there is we're trying to share electrons. We don't want to have either of them lose the electron, but they've also got to be good enough at getting an electron that they can share it, not so good that they steal it. Now, that means that both of them are going to have a high ionization energy and a high electron affinity. This prevents it from being stolen. This one is the one that lets them grab the neighbors and force the sharing to occur. Now, for metallic bonding, we want to be able to share the electron. We don't want to be keeping it around ourselves at all, so we can't have any feeling of ownership there. We're going to have a low ionization energy. It's easy to take it away. You don't really care if they take the electron from you. Low electron affinity. You don't care too much about grabbing somebody else's electron either, though. So it's a bunch of people who don't really care about what they're holding, but they're not surrounded by thieves. So they're really okay with just sharing that item. And that item in this case happens to be the electron.